When a useful new technology comes out, companies that are in a position to adopt that new technology can gain an edge over competitors who are not in a position to adopt that technology. As our industry grows and moves faster, these kinds of changes are coming faster. Some recent examples are Docker, ReactJS, and Kubernetes. Evolutionary Architecture supports incremental guided change as a first principle along multiple dimensions. A company with an evolutionary architecture is structured to evolve in response to changes inside the company, such as a decision to change the product, or changes outside the company, such as the emergence of a technology like Docker. Neal Ford is an architect at ThoughtWorks and one of the creators of the evolutionary architecture concept, and he joins the show today to discuss what evolutionary architecture means and how a company can implement it. Neal is also giving a 2-day training at the O'Reilly OSCON conference, May 8th through 9th. O'Reilly has been a great sponsor of Software Engineering Daily by giving me tickets to their conferences and connecting me with speakers. So if you're interested in checking out an O'Reilly conference, you may want to give OSCON a shot. I hope you enjoy this episode. When I'm choosing the tools for my side projects, the first thing that I look for is ease of use. That's why I love MongoDB. It is the most popular non-relational database, and it is super easy to use. At the beginning of a project, I often don't know the shape of my objects, and Mongo makes it easy to evolve the database schema as I like over time. Over time, as my project gets popular, I'm going to need to scale, and thankfully, MongoDB has built-in horizontal scalability, but configuration and database maintenance aren't really what I want to spend my time on. Thankfully, MongoDB Atlas was released in 2016. MongoDB Atlas is the easiest way to get access to MongoDB without having to run the database yourself. You pay only for what you use, from small projects all the way up to large production deployments. To try MongoDB Atlas today, go to mongodb.com/sedaily and get a free $25 in credit. Use promo code GOATLAS25 to get that $25 in free credit. Atlas is the only hosted MongoDB service built by the engineers behind the database, the company MongoDB. With Atlas, you get end-to-end encryption, you get VPC peering, you get access to the latest releases, and for a limited time, you can go to mongodb.com/sedaily, enter promo code GOATLAS25, and get that $25 in credit, and get started with MongoDB Atlas. Thanks to MongoDB for being a new sponsor of Software Engineering Daily, and thanks for being the database behind a lot of my favorite side projects in the past. We're really happy to have MongoDB as a new sponsor of Software Engineering Daily. Neal Ford is an architect at ThoughtWorks. Neal, welcome to Software Engineering Daily.
Thanks for having me. I'm glad to be here.
Today we're going to talk about architecture, specifically evolutionary architecture, which is something that you've been giving talks on for a while. You describe evolutionary architecture as an architecture that supports incremental, guided change as a first principle along multiple dimensions. And I think everybody who is listening will agree that sounds great. We know that our software is going to be changing all the time. It's constantly evolving. If we know that our software is changing and that our world is dynamic, if everybody agrees on those things, what is the significance of the term evolutionary architecture? Why do we need to define this thing? It seems like something everybody wants already.
Well, everybody wants it. The question then becomes, how do you achieve this? What are the concrete engineering practices that lead you to this? So one of the questions so I'm also writing a book about this. And so toward that end, the definition you've read is now one word out of date. We've changed the word along to across. So an evolutionary architecture supports incremental guided change across multiple dimensions. So here's what we're trying to do. The purpose of this book and all these talks in one sentence is, so one of the things that architects are always trying to evaluate are what sort of architectural characteristics do they need to support, all these ilities that we commonly talk about. And that's really one of the distinguishing characteristics between architecture and coding and design is the looking at architecture patterns and trying to assess what kind of entities these support. So here's the one definition of one sentence definition of what we're trying to do. We're trying to make evolvability a first-class entity in software. And so we're trying to answer the question, what would it take to make evolvability one of those entities that as an architect you can plan for, you can choose what sort of architectural pattern you're going to use, and more importantly, once you've chosen those core entities, those core characteristics you want to, that you've chosen the architecture for, how do you keep them from degrading over time as your system changes in unexpected ways? So we know that systems are going to change in unexpected ways. We're talking about how to prevent degradation over time.
We've done numerous shows on the topic of microservices architecture. What's the connection between microservices architecture and evolutionary architecture?
Okay, well, that's a good question. So let's think for a second about the inherent evolvability of an architectural pattern. So, for example, layered architecture, which everyone's familiar with, layers of separation of concerns. So you can evolve that architecture by swapping out layers. So, for example, if I have a persistence layer, I can evolve the persistence mechanism of my architecture by swapping out that layer. So you can think that that architecture allows you to evolve sort of along one dimension, which is that technical architecture dimension. And it turns out that most architecture patterns let you evolve by changing discrete parts in well-defined ways. In fact, that's one of the reasons we build software architecture, so we can change things without breaking everything, which is why we don't purposely build big ball of muds anymore. And the thing that's unique about microservices is because one of the big emphasis in microservices is rather than try to create sharing and try to emphasize the technical architecture is subsumed to the domain perspective within microservices. So each service is its own bounded context and highly decoupled from all the other services. And so this is a good example for us of an evolutionary architecture because it supports change across multiple dimensions. So we would argue that every architecture supports change along at least one dimension. That's why you use software architectures to be able to change parts without breaking the others. We're interested in architectures that support change across multiple dimensions, like microservices. And it's not the only one, but it's certainly a good exemplar of this kind of evolutionary architecture because you can literally change out one service for another without breaking anything else in a well-designed microservice architecture, and therefore evolution is much easier.
One thing I always think about in conversations about architecture when I have conversations about architecture with people on the show is the degree to which the technologies that we're working with shape the types of architectures we build. So, you look 10 or 20 years ago, a lot of people are building stuff with Java or .NET, and then you go forward in time, it's Ruby on Rails. And you go forward a little more, it's Node.js. Are there certain architectures that these frameworks push us towards creating, or do we? It's the
opposite.
It's the
opposite because no architecture springs to life without the context in which it was created. So let's play a little mind experiment for a second. Let's go back 10 years and pitch a microservice architecture in a large organization. So I'm going to go to the head of operations and say, okay, look, I need 100 pristine Windows boxes because I'm going to run each service all by itself on that box because I don't want any coupling or any sort of interference, and I will be able to evolve those things independently. They would smack you on the head and run you out of there so fast you wouldn't be able to see because you can't afford 100 licenses for commercial operating systems just so you can do isolation for everyone. So if you look at the architectures that we built 10 years ago, they all heavily favor shared resources. That's part of the big idea of a Java virtual machine and thread pooling and database connection pooling. It's all these shared resource architectures because computing resources were scarce and expensive and commercial almost universally. But I would argue one of the reasons that microservices exist is because over time, Linux became good enough for most large corporations, which was step one. But then step two was the popularization of tools like Puppet and Chef and Ansible and then later Docker, which means that now Linux is operationally free, which means now there's no real cost, either monetarily or operationally, from giving every developer their own pristine environment that only has the stuff they need in it. So one of the problems with any kind of shared resource architecture, even if you have really good isolation, they're still going to fight over resources. One of the big gnarly jobs a decade ago was getting application servers to run on machines and then having them not fight over memory or I/O or some other resource. If everybody's running in their own pristine operating system, you don't have that problem anymore. But see, that architecture wasn't feasible a decade ago. So it's a little like art. And boy, this is a weird metaphor, but you can't understand art outside of its context either. I mean, if you look at an Andy Warhol painting just as a completely abstract thing, it's silly. You know, it's a lithograph of Marilyn Monroe. But if you understand the context in which that was created, you understand why it's art. The same thing is true of architecture. You can't divorce it from the physical constraints and the software development ecosystem that spawned that architecture. And that actually is one of the reasons why we're interested in investigating this idea of an evolutionary architecture, because that software development ecosystem is dynamic. So if you think about all the things that make up how we build software, the frameworks and tools and best practices and all those things, it makes up an ecosystem. But it's extremely dynamic and it changes in unexpected ways all the time. So if you're an enterprise architect 2 years ago and you wrote a 5-year plan that didn't include Docker, you can now take that 5-year plan and wad it up and throw it away, because the thing you're trying to plan against can fundamentally shift without notifying you and in ways that you can never imagine.
Okay, this Docker example, you described Docker as an example of technology that forced companies to reframe that 1-year architectural plan that lots of companies have at any given time, because the potential gains that they could get out of Docker were so significant.
Well, it's not just Docker. Docker was the last piece of a puzzle that allowed people to do that.
Okay. Well, in any case, Docker was this unknown to most companies. So
exactly.
So how do you prepare for that type of thing? I mean, Docker kind of came out of the blue at this container orchestration, or this container level that, you know, most companies were not even thinking about. So how can you prepare for that sort of thing? Because that's almost like such a random existential place for a new technology to come out of.
Well, we believe that predictability is shot in software, and you shouldn't try to predict things anymore. You should build architectures that can adapt to change cleanly and evolve as the ecosystem around them evolves. That's why we're talking about evolutionary architecture. You can't predict the future. You can't future-proof against it, so you need to embrace it as much as possible and build architectures that can accommodate weird change as much as you can.
I want to touch on one more semantic issue, since we're on the topic of architectures, and you've been around in the architecture industry for a while. I had Jonas Bonner on recently, and we were talking about this term microservice versus service-oriented architecture. And yes, this is a semantic discussion that we could beat to death, but it is interesting that we created this new name, microservices, for something that already existed, service-oriented architecture. And you know, people do touch.
This is a misunderstanding. So the original article that brought up microservices was written by Martin Fowler and James Lewis, both of my colleagues. And they actually made a point in the article, and everybody forgot this part, that the word microservice is a label, not a description. So it doesn't mean that every service has to be teeny tiny. They had to give it some name, and they labeled it microservices to contrast from service-oriented architecture, which is a well-known gargantuan, very heavy moving, lots of moving parts thing. And a lot of people mistake that, and they think it's a description, and then it forces them to do crazy things like trying to break services down beyond a reasonable size just so that they can achieve this goal, I'm making air quotes here, goal of becoming microservices.
Every software project uses email. Every time an e-commerce site processes a transaction, or a user makes a comment on a social network, email notifications are sent. SparkPost provides email delivery services for apps and websites. To try SparkPost and send 100,000 emails a month for free, go to pages.sparkpost.com/sedaily. SparkPost has a range of pricing options, from free self-service packages to sophisticated enterprise support and services. Start sending emails to your users today. Go to pages.sparkpost.com/sedaily to send 100,000 emails a month for free. Thanks to SparkPost for being a new sponsor of Software Engineering Daily. And if you want to send 100,000 emails a month for free. Go to pages.sparkpost.com/sedaily. I mean, so why did we have that? Was it the idea that the service-oriented architecture, if you build a service-oriented architecture, your API for a service in that world is really, really wide, and a microservice, you have a much more thin...
Well, it's much more than that. Service-oriented architecture is a very distinctive industry definition for many, many years, which featured heavy use of service taxonomy, this idea of building top-level abstract business rules, very often in some sort of hideous tool like BPEL or BPM engine or some awful enterprise-level tool like that. Then having a team of developers building these concrete shared services that are meant to be stitched together with orchestration via an enterprise service bus. So there's a very distinctive definition. So what you're talking about here is capital SOA versus lowercase SOA. If you're trying to describe something as a service-oriented architecture, meaning that it is an architecture oriented around services, then that encompasses microservices, service-oriented architecture, what we call service-based architecture, and most event-driven architectures as well. If you talk about SOA with a capital SOA, it's a very defined thing in the architecture world a decade ago that has these specific moving parts and the specific kind of tooling and support around it.
Okay.
So, for example, you'd never have an enterprise service bus in a microservice architecture because it violates one of the core premises of that architecture, which is a bounded context. And putting some of your orchestration or choreography in an enterprise service bus breaks your bounded context. It's the same effect of smearing your bounded context across your integration architecture. But you would never, ever build a capital SOA architecture without an enterprise service bus, because that's where most of the world lives.
Okay, this is something I don't have much perspective on because I've heard of this enterprise service bus. People don't really like it or whatever it was. But today people talk about, you do have a messaging layer. And I mean, you talk about that in evolutionary architecture. You advocate for like a pub sub type of messaging layer.
Messaging is great.
Right. Okay, so what's the difference between this historical relic of the enterprise service bus? What does that actually mean? Because I think there's a lot of people that listen to this podcast, they've probably heard that term on some of the episodes where people, with interviews with people who have been around for a while, and they say this term and like, I don't know what it means.
So this was a pattern that was defined in the Enterprise Integration Patterns book by Gregor Hope and Bobby Wolf, this enterprise service bus pattern. So the idea, and this is a kind of a natural instinct that architects have. So let's talk about where this enterprise service bus thing came from. Because again, anything out of context is just kind of a bunch of facts. So one of the problems you run into very quickly in integration architecture is you have application A and it speaks HTTP, and you have application B and it speaks SOAP, and application C speaks message queue. And now I need to get these guys to talk to one another. And it's a disaster if every single thing has to understand the protocol of every other single thing, particularly as you get into complex integration architectures where you don't control some of these things because you've merged with another company and now you have to integrate with their systems. And so architects created these hubs. And a hub paves over all those differences. A little like protocol transformation for you. Take a JSON and transform it to XML, or take XML and serialize it into a Java object and back and forth. And that's a useful thing. But then they got a little crazy because they said, well, we solved this problem by pushing everything to the center of the universe. What else can we push to the center of the universe? So the idea of an enterprise service bus is that the idea in a service-oriented architecture with an enterprise service bus is you have a team of developers, and I always envision them being in a basement somewhere in a windowless room, who are writing the shared enterprise services, because the idea was, in that time, you know what? We have a discrete number of things that we do as a company, and if we can write reusable pieces around everything we do as a company, eventually we'll stop writing code and new applications will just be stitching together these little shared things that represent all of our ideas within the company. And so the idea was these dungeon dweller developers are writing all these little shared things, and then the people at the top of the architecture are using this business process execution language tool, which lets you draw lines between boxes, and then it vomits out 10,000 lines of XML that you feed to some engine that manages all the messaging between these components. So they're defining all these new business processes. And so the enterprise service bus therefore define all of the workflow of your application. This is how services get stitched together. It controls all the transformation between all the weird endpoint protocol things that you have. It also does things like clustering and availability. So that is the intelligence of your application is in that enterprise service bus. So it really is a service bus, but it is intelligent in that critical business processes live there and only there.
It sounds like we had the ideas kind of right. It's just what we had wrong was how dense the layers of abstraction that we thought we needed, I guess, because we wanted this, at the highest level, it's drawing arrows between boxes. And then
to translate. Turns out it's a terrible idea that sounds like a good idea.
Yes.
Did you ever hear of the IBM San Francisco Project?
No, what is that?
So this is one of those stories that every architect should know. In fact, I'm doing a talk next year called Stories Every Architect Should Know. And I've got 12 of them so far, and this is one of them. It's the story of the IBM San Francisco Project. So in the early 2000s, IBM looked around and they said, every stinking business application we see looks the same, so we're going to write one last business application.
Oh, no.
And this is called the San Francisco Project. And we're going to write an inventory module and a P&L module. And this is going to be so cool that any company can take it and just tweak some properties, tweak this property and tweak this property and model exactly their business process. How well do you think that worked?
Poorly.
Extremely poorly. They released 2 full modules before they realized this is the stupidest idea ever, because companies don't build reusable things. They build one-off everything. Building reusable code is really, really hard. The few companies that were successful with service-oriented architecture, it was this long, painful process of how do you actually build things that are reusable. And it turns out nothing you build is all that reusable in the software world. Everything turns out being bespoke. And the problem with an enterprise service bus, so let's say that you have this architecture, and let's say that you've been stunningly successful with this architecture, and you're running with this architecture right now. And I need to make a change to customer. Where does customer live in the service-oriented architecture? Well, part of customer lives in, part of him lives in the database. Part of him lives in the top-level business services that are extremely abstract. Part of him lives in the enterprise service bus because that's where all the workflow around customer lives. Part of him used in this constellation of reusable services that we're trying to use. So now I need to make a change to customer. And now I've got to coordinate between 20 people in my company to do that. How agile is that? Not very. So if you'll notice, one side effect of modern architectures, particularly microservices, is they're primarily domain-centric rather than technical architecture-centric. So service-oriented architecture is almost the fetishization of technical architecture as a thing to play with. So one of the hazards that I think developers fall into all over the place in the world is this meme that I wrangled called meta work is more interesting than work. Every developer listening to this podcast would rather build a framework than use a framework to build something useful. Because that's way more interesting. Because here's the sad truth of our industry. So if you really boil it down, so we're recording this right before Christmas, so you're going to bump into your grandparents over Christmas. And when you really boil it down and need to explain it to your grandparents, your job is, I take things from web pages and put them in databases, and I take things from databases and put them on web pages. Yeah, there's some details in there, but at the end of the day, that's what it is for a lot of places. And when you've done that 20 or 30 times, it gets kind of boring. You know what's not boring? Building a new framework to do something. And so meta work is way more interesting than work. And so people fall into this all the time. And service-oriented architecture is a great example of that.
I kind of want to zoom out because you said something interesting about the fact that the San Francisco project didn't work, this big monolith that IBM was going to build and say, okay, this is what everybody's going to make their application into. And you said that it doesn't work because you can't make a one-size-fits-all solution, but that's kind of what AWS did, and successfully. AWS was able to say, okay, here's some primitives that every architecture is going to need. The difference, perhaps, is that it's easier to compose them, it's easier to pick and choose, and it's self-serve, so you don't have these types of problems that you're talking about where you have to orchestrate a gigantic change in this tightly coupled giant organization. You have loosely coupled things that you can just pick from a menu. Would you say that's accurate?
Oh, and they're trying to achieve a completely different thing, too. They're trying to become your operations center, which is a completely different level of abstraction from we're trying to be your application. I mean, ERP packages try to do sort of the same thing that San Francisco Project did. And not surprisingly, very few of them are true success stories because businesses are complex things. You know, if every business were at really exactly the same at its core, then we would have 2 insurance companies because they would compete on price and everything else would be commodity. We have hundreds and thousands of insurance companies, and all of them are snowflakes the way they do things, and part of that's the way they differentiate themselves. So what Amazon did was a clever thing, which is abstract all the operational aspects of the architecture into this set of APIs you can consume. And that's completely different from what San Francisco Project did. They were trying to build business applications where you tweak properties and build profit and loss and, invoicing and all these top-level business things.
Okay, well, let's get back to the idea of evolutionary architecture. What are the different things that can cause a company to need to evolve? Why do we need to bake in this evolutionary architecture at a really fundamental level?
Well, for some companies and more companies, your ability to get things out into the marketplace faster becomes a business differentiator. So there are a few companies out there that are doing continuous deployment, and it takes a fair amount of engineering sophistication to do that, but they're doing that because they're in markets that are extremely competitive. So one of the things that you measure in the continuous delivery world is this metric called cycle time. And cycle time is a measurement of when I start working on some new feature, that's when the clock starts. The clock stops when that new feature is running in production. So one of the goals of cycle time, or one of the goals of continuous delivery is make cycle time shorter and shorter and shorter by using automation and DevOps and a bunch of other techniques that have been developed in the continuous delivery world. Some companies now view cycle time as a business differentiator. So there's a great quote by science fiction author William Gibson that the future is already here, it's just not evenly distributed. And the best example I've ever heard of this happened a little over a year ago when they had elections in India. India is the largest electorate on earth, and some parts are, let's say, intensely rural and hard to get to. And so one of the candidates ended up doing electioneering via a hologram. So kind of like the Tupac hologram, this hologram would show up at election events and talk to people, make speeches. And one of the things that the hologram was promising people was indoor plumbing. And you know the future's already here, it's just not evenly distributed when the hologram promises you indoor plumbing. But see, a lot of companies are like this because they view software purely as overhead. And why would I care for better engineering efficiency and overhead? But then some company comes along that does care about that. And all of a sudden, your 6-week cycle time, they have a 6-hour cycle time, and you start doing things like marketing campaigns, and they're beating your brains out because they can do things like A/B testing and do multivariate testing and get multiple releases out in a short amount of time and respond to the market a lot faster. There was a famous article in Fortune a couple of years ago now, I think, called Every Company is Now a Software Company. And their point was, if you're Delta Airlines and your iPad app sucks, that's going to be bad for your stock price. So at some level, engineering efficiency is going to become one of those things you value companies for. But there are still a lot of industries where they're kind of fat and happy and don't care about efficiency that much. But innovators are coming along and going to nab you with the Innovators Dilemma by doing some stuff better.
Now, the big question I have with these types of conversations is there are plenty of companies who are younger, newer, fresher companies. Maybe they grew up on the cloud, and it's been easier for them to adopt things like continuous deployment and microservices and Docker and whatnot, and they've been writing tests since the beginning, so they have this testing infrastructure that works really well. There are other companies that are older, and they didn't grow up in this time where they knew that software was going to be a big differentiator, so maybe they didn't put a lot of emphasis on software architecture, and they've ended up with something that is a big ball of mud or some sort of giant monolithic architecture where the test coverage is really sparse, and they want to get to this point where they're more evolutionary. And this is like, I was at the DevOps Enterprise Summit, and this was like a huge point of the discussion was like, how do you get from this big monolithic or big ball of mud, whatever your negative situation is, how do you get out of that? Do you start by writing tons and tons of tests? Do you break off a small piece of the architecture and turn it into a microservice. What are your options if you find yourself in this situation where you're in an architecture that is not evolutionary and you want to get towards an evolutionary architecture?
Well, that's a large part of my professional life. So this is what we do a lot for our clients. I've been doing this a lot over the last few years. And so there are a variety of approaches you can take. So one of the things that we talk about, and we haven't touched on around this evolutionary architecture definition that is pertinent to this part of the conversation, is the guided change part of our definition there. Because one of the co-authors of our book is Rebecca Parsons. She has our CTO, she has some experience in evolutionary computing. And there's this concept in evolutionary computing called a fitness function. So if you're designing an algorithm that's going to evolve over time into something better, the fitness function is what determines, is this generation better than the last one? So this is whatever function you've defined to say, okay, this one is closer to achieving the goal that I ultimately want this evolutionary thing to achieve. And so we're borrowing this fitness function metaphor by saying, okay, once you've identified the really important ilities in your architecture that you chose that architecture for, you want to allow the piece of the architecture to evolve as freely as possible, but you don't want to degrade those ilities. And so what we suggest is building tests and metrics and other sorts of verification mechanisms around those ilities in the form of fitness functions. So that's the name we're giving this family of things to protect things against breaking. So you could use this concept of fitness functions in this kind of refactoring, restructuring exercise of a big kind of awful monolith into something that's a lot more flexible. So one of the things you can do is build tests that test kind of black box testing one part of the system. So, customer transactions. Let's just take that as kind of a black box and build a kind of a fitness function test that just tests that behavior, nothing about the implementation or anything like that. And now as you start breaking that apart into smaller pieces, you can still run this test and verify that the behavior is still there. In fact, there's this really slick framework that is really more designed for lower level coding, but would work great for this. This is framework that was invented by the GitHub guys called Scientist. And it's a kind of a feature toggle framework. So let me describe this, and I'll come back to the example we were given before. So what Scientist allows you to do is try out new code, but make sure that it doesn't break anything. So let's say that I've just rewritten a part of my system that calculates tax rates. And I want to replace the existing tax rate calculation, but I want to make sure there are no regressions. I haven't broken anything. What Scientist allows you to do, once you put this, it's a little framework that you put in place, you have a try block and a use block. And the use block executes the old code. The try block, to some small percentage of new users, executes the new algorithm. So maybe 1% of users gets the new one. And it also executes the old algorithm in parallel and then compares the results. And if you ever get anything other than what the old one would have returned, it always returns the old value. So the worst case scenario is you get what you would have gotten before. But what this lets you do is displace things very slowly without breaking stuff. And that's exactly what that integration test would serve as you start decomposing things. And so the first trick is to take your big ball of mud, whatever it is, and regardless of, so the first assessment is feasibility. Is it worth actually trying to restructure this ball of mud, or should we just start over with something better? And the first way to assess that is try to establish better modularity in the code that you already have. Because those modularity boundaries will tell you how easy it's eventually going to be to break it apart into something more reasonable and less coupled. So, and even if you reach the end of that and you decide not to restructure your architecture, you're still doing you're still a force for good because you have better modularity within your architecture. And once you get to better modularity, that'll tell you the feasibility of breaking things apart.
How do you look at that architecture and define the points of modularity if you're looking at a big monolith or ball of mud architecture?
Well, a lot of tools that you can do assessment for afferent and efferent coupling between the packages and classes within the architecture to determine what the coupling is and how much coupling there is between packages and modules within your architecture. So there are metrics, tools, and visualizations that will help you assess this stuff.
Okay.
X-Ray is a good example of one that runs inside Eclipse in Java. Independ is a good example of one that you can use in .NET to assess the dependency matrix between things in the .NET ecosystem. So there are tools in most platforms that allow you to do that.
So you described something called this fitness function. You described it as core to how you evolve as a company. Every architecture has this fitness function that defines the things that it needs to emphasize. When I think about latency and reliability and security, these seem like things that every architecture needs. So how do I define the fitness function? How do I decide what are the things that are most important to me?
Well, if I were the perfect architect, then every architecture that I build would be extremely scalable, it'd be highly performant, it'd be elastic, it would be resilient, it would have high security, it would have extremely high accessibility. I could go on and on and on. No architecture's like that. You never build perfect architectures. The reason you choose one architecture pattern over the other is that, so if you look at the entire constellation of entities that you can support, you cannot support all of them. In fact, some of them are counter to one another. Very often performance and scalability are at odds with one another. So you have to choose some things that you're building this architecture for, the purpose that you're building this architecture. So when I do this exercise with people, I give them a problem and say, pick 3 primary entities and 3 secondary entities that you think this architecture needs to support above all others. And then that's the reason you would pick a particular architecture pattern. So why would you pick a layered architecture versus event-driven architecture versus a microservices architecture versus a microkernel architecture? Well, part of the reason you choose those architecture patterns is because they support some of those characteristics better than others, and you try to map what characteristics do I need to support to what kind of architecture pattern am I using to build this. Sorry, there's a really loud thing outside my window. He's literally right outside my window. Yeah. You can't support everything. And so this idea of a fitness function, you'll have several of them. It's whatever, because the worst thing you can do for an architecture is to choose a specific architecture because you want it to support certain entities. So for example, one of the reasons you choose a layered architecture is it supports this ability to swap out layers so that I could swap out my persistence layer and choose to go for Ibis rather than Hibernate. But then the first thing you do in your layered architecture is allow people from the presentation layer to directly access the database layer and bypass the layers.
Okay.
So all you've done is build a big ball of mud because now the layers are meaningless because the reason you put them in there are no longer function for that purpose because now you've created coupling points between places that are going to prevent you from doing this kind of change. So whenever you create an architecture, you defined it around some certain entities, you don't want that to degrade over time and turn into a big ball of mud. And that's part of this idea of fitness functions around these entities is define why am I building this architecture and how can I protect it over time as it grows, sometimes in unexpected ways.
Okay, so once we get to the evolutionary architecture in an ideal world, we have this incremental guided change. What is the happy path for how a change would work in that world? Like, what if we think about the ideal evolutionary architecture? How does change work in that type of environment?
So, okay, I'll give you an example. So, this is the example that kind of runs through the book. Is this company we're calling WidgetCo? So let's say you're WidgetCo and you have a catalog site with widgets on it. So, and you allow your users to star rate widgets. So you have a star rating service that runs within your architecture. Then one day you come up with a better star rating service that does half-star ratings, and so you put it live in your architecture. You don't force any of your services to use it, you just make that capability available. Those other teams, as they improve themselves and want to use better star ratings, start migrating over to the new star rating service until no one is using the old star rating service anymore. And this is one of the magic tricks Netflix taught us about architecture. You monitor not only services, but also the routing between services, and any service that hasn't been routed to in a set amount of time automatically gets disintegrated out of the architecture. So that's incremental change at the architectural level. I put a new feature live alongside an existing feature. I allowed people to migrate to it at their own time, and then I got rid of the old stuff that I didn't need anymore. But part of this is also the enabling ability to do things like A/B testing or multivariate testing. Because one of the things you need to be able to do is evolve your architecture. If I want to try out something new against my users, I need to be able to evolve some behavior of my architecture, at least temporarily, and give some users one view and some the other so I can do A/B testing against them and find out where should I really go. So one of the advanced capabilities that companies really want is this ability to do things like hypothesis-driven development. Rather than have business analysts go into a windowless conference room somewhere and brainstorm what's the next thing we should build, we should vet it against our users and see what they actually want us to build. So there's this whole movement that comes from lean enterprise, this idea of hypothesis-driven development. And so let me give you a case study that demonstrates that. So there's this software company in Germany that made a car listing app for iOS. And it was a mature agile project, but this is something that happens in a lot of mature agile projects in that business analysts are still coming up with new features that they want seen. And every new feature in isolation seems to make sense, but in aggregate, they start dragging down usability and other sorts of aspects of the application. Then the worst possible thing started happening in this company. Their number of users started falling off. And now an internal debate started raging within the company. What do our users actually want out of this application? Do they want more listings so you get better information density? They want better structured so they want better curation? Or they want better prioritization so they see the things that they want more exactly? They don't know the answer to this question, and so they did hypothesis-driven development and released 3 versions of their application to actually find out what their users wanted, and they found out that what their users wanted, which I believe was better structure, and that gave them guidance on what we should continue to build in the future because now we know what our users actually want. But part of that capability is the ability to evolve your architecture and make things, put them alongside each other and evolve to them over time. So this is really a building block for a lot of advanced capabilities that people would like to have at the architectural level. And this gets back to the question you asked earlier, why would a company want this? Well, you might want to be able to do multivariate testing or A/B testing or do some canary releasing or some of these other kind of modern DevOps practices, some of which evolutionary architecture makes a lot easier.
I think when you mentioned Netflix, you were describing the way that they use the circuit breaker pattern to help with change management. Is that accurate?
Well, yeah, you can use, they do monitoring to manage. This is actually slightly different than the circuit breaker.
Okay.
They're just using monitoring to look at the age of services and when was the last time that service got routed to. Because the logic being, if this service normally gets routed to, 1,500 times a day and no one's routed to it in the last 2 weeks, probably no one's using it anymore.
Software Engineering Daily has 20,000 engineers listening Monday through Friday. If you are hiring, or if you have a product that you would like to get into the hands of engineers, send me an email, jeff@softwareengineeringdaily.com. This podcast is sustained by the advertisers, and if you would like to become one, or even if you're just curious and you want to learn more, send me an email, jeff@softwareengineeringdaily.com. Thanks for listening. I mean, we're talking these broad architectural strokes, but I like it when you are talking about a very specific technical aspect that helps support this evolutionary architecture, this higher level thing. Can you talk about that emphasis on routing a little bit more?
Well, sure. I mean, in a microservice kind of world, an application really consists of which instances of services you're routing through. And so you could very easily create a scenario where I want to try out some new behavior, like a different behavior for star ratings. And so just route 1% of people through enhanced star ratings and the other 99% through the regular star ratings. So you don't even have to use feature toggles in that kind of world. You can just do routing. Have one, half star rating service and the other just a regular star rating service. A lot of times in microservices, when you define applications, you define, go through this kind of instance. And you can set up a canary release for, some small percentage and then route to them instead, and then gather statistics as to, some sort of metric as to was this better than the last one.
Okay, I'm sorry. I was confused because I thought with the circuit breaker, I thought you were talking about some sort of failover in the event that a service rollout went poorly.
Well, that's a super common pattern in that world, but that's
sure.
Using circuit breaker, and I mean there's a lot of elastic tricks you can do with elastic scale and resiliency and that kind of stuff. A lot of which you don't have to have fancy frameworks with. The guy I do a lot of work with from a content perspective, Mark Richards, has a great talk about building reactive architectures using nothing but message queues. So you don't need fancy frameworks to do that. It's all just how you design things.
Okay, well, let's go there. Let's talk a little bit more about message infrastructure. You describe the message broker infrastructure as very useful to decoupling an architecture. Why is that message broker layer so useful?
Well, a message broker is still useful in the world where you have lots of integration points. So I would use a message broker, an enterprise service bus or something like that. If my management came to me and said, our corporate plan is to engage heavily in mergers and acquisitions over the next 3 years, I would sprint toward a message broker at ESB because it's great for paving over weird integration point issues. So I've got something that talks RMI over IOP and some other thing that speaks some ancient Corba protocol, and I want to pave over all that stuff. And so some sort of a message broker or enterprise service bus allows me to do that very easily.
Well, so if let's say we were in that situation you discussed earlier, where you have the big ball of mud or some crazy monolithic layered architecture, how hard is it to implement a message broker in that type of world?
Well, you're talking about just a message queue of some kind?
Yeah. Well, I guess. How do you indoctrinate the architecture with that?
If you have a monolith, so let's say you have a layered architecture or something like that, and you need parallel processing abilities, you can just add a message queue to that and start making calls from the monolith into the message queue and back.
Okay.
But they're fundamentally two different kinds of event-driven architectures: a mediated event-driven architecture and a broker event-driven architecture. A broker one where each service is essentially autonomous from one another. So let's say I'm in an insurance company and I have some sort of some workflow, business process workflow, and so change of address. So a change of address changes the address and then posts to a message queue where people who are interested in change of address are subscribing, and so maybe update claims and subscribes to that and is interested, so they update themselves and then post to another message queue for people who are interested in update claims. So that's a super highly decoupled, very almost stateless, where each event processor is essentially autonomous, versus a mediated event-driven architecture where you have a mediator, which could be something like an enterprise service bus that knows what the steps of the business workflow are and can make sure that transactional behaviors happen and all that kind of stuff. So either of those you can latch on to. That's a perfectly normal hybrid architecture if you have some sort of like a layered architecture, monolithic architecture of some kind, and you need some sort of better parallel performance, for example. So if I had commodities trading and I needed to do a bunch of stuff in parallel, then you could have the monolith basically have the monolith post an event to a message queue somewhere and then have the event processor pick that up and then get it back to the monolith for the results.
What about the database layer? What are some principles for maintaining the right database abstractions in an evolutionary architecture?
Well, so the big thing about databases and evolutionary architecture is you have to be able to evolve your database schemas alongside your architecture. And that's tricky because a lot of the common engineering practices we have in the development world have not penetrated into the DBA world at all. There is, however, fortunately, good recourse for this. There's a book that came out. It's at its 10-year anniversary right now. And I want to promote this thing to the moon. It's by Scott Amler and Pramod Satterlage. It's called Refactoring Databases, but the subtitle is called Evolutionary Database Design. And I bumped into Pramod recently, and I told him, you need to re-release this book, make one small change, just flip the title and the subtitle, because everybody and their brother would buy a book called Evolutionary Database Design, subtitled Refactoring Databases. So there are techniques to be able to evolve your database schema very cleanly, just like you evolve your architecture. But it requires some things like testing and some other agile practices that are a little foreign to some organizations. We find less penetration for kind of agile techniques in DBAs than in most development shops. But all those techniques are there. And you can, in fact, do things like support evolving your architecture and evolve around your database schema so that you need to support two schemas in parallel. There are plenty good techniques that allow you to do that.
You talk about the hazards of the single centralized database. Why is that hazardous and what can go wrong?
Well, it's just one giant coupling point. So probably not surprising to many of the people who are listening to this right now, one of the keys to evolving stuff is having highly decoupled systems. And one monolithic database is the opposite of a highly decoupled system, especially if you're using that database. It also is an integration point for your architecture, which happens in a lot of architectures because, well, everybody's talking to the same database anyway, and these two applications need to chat with one another. Why not just let them do it through the database? Because they're already talking to the same database anyway. But then you realize 3 or 4 years down the road, oh no, I need to change the schema for one of these applications, but I cannot because 3 other applications use that schema as an integration point. So what you've done there is fossilize that schema all through your application and create a coupling point that's really hard to break apart. And so that's what we call temporal coupling, or coupling to database stuff. It's just as insidious as having a big ball of mud in terms of classes. No matter how cleanly you can evolve your architecture, if you can't evolve your database, then you probably can't evolve your application, because realistic applications also have databases.
Can you talk about some of the patterns to decentralizing databases if a company ends up with a centralized database?
Well, sure. I mean, it's the same thing you do with your monolith. You do modularity. So basically what you do is go through some sort of domain-driven design or some sort of entity discovery exercise and start trying to stop doing coordination of the database. So start doing, break apart the coordination you have there and move it up to the architectural level and do messaging. So instead of just sharing a table rows to do integration, change that to messaging so that now the applications own their database and they send messages back and forth when they want to collaborate for data like that. And increasing the modularity in your database alongside increasing the modularity in your code base. What you'll often find in big monolithic applications is that there are some pretty fat entities kind of floating around there, the things that you're building these applications for. And you'll see big coupling points around the source code, but also around the data schemas around those core concepts. This is really what domain-driven design is trying to get at when they do an analysis of some problem spaces, try to identify those domain-bounded contexts where the similar kinds of work happen, and then refactor toward those things. And so the idea, if you have a monolithic database and you have a monolithic architecture, here's the other piece of advice from before, start with a small number of larger services first. Don't try to take the boulder that is your monolith and reduce it to gravel in one step. Create some big size rocks along the way. And basically what I mean by that is look at your existing monolith and look for seams within your existing monolith. And those seams are going to be places where, all these things belong together because they're all related to customers or orders or catalog or something. Those same kind of seams will exist in your database. Look for things like transactional boundaries. Where are we doing transactions within this architecture? Because those show you where a lot of those business seams are, as to what things are wrapped together in transactions. And that'll help you identify both architectural and data kind of modularity that you can kind of gradually move toward and untangle yourself from the big ball of mud.
Now, is it problematic to have data duplicated in different databases? Because this is a conversation I've heard with along people who are decentralizing their databases. Do you want to get to a point where you can have inconsistencies between different databases? Well,
so what's the value of having canonical data versus having duplication? So that's really the question that you should ask yourself at the architectural level. And what a lot of microservices have realized is that the cost of duplication is way less than the coordination cost of trying to keep a canonical source of truth somewhere. So one of the things that I think architects do incorrectly, this is one of the natural instincts of architects to try to categorize and taxonomize the world, is that you look at catalog and it has an item. And you look at shopping cart and it has an item. And you think, oh, those are both called item. Those must be the same thing. So I should create one reusable thing called item. The shopping cart could use it and so can catalog. Here's the problem with that. Catalog needs different stuff from item than shopping cart does. And so if you try to use it for the same things, you end up bolting on stuff for both of them. So here's the ironic thing about that. The more reusable something is, the less usable it is. Meaning that something that's really super generic, you have to do a lot of work to use it for one instance of something. And so what the microservices guys realize is, look, those two things may incidentally have the same name, but they're used for different purposes. So don't try to reuse that. Just duplicate whatever that characteristic is and then send messages back and forth, for one thing versus the other and hydrate one or the other. And so there's a lot less concern in the microservices world of finding the single source of truth for stuff, because very often what that creates is a coupling point that is actually less desirable from an architectural standpoint than duplication.
Well, we're nearing the end of our time, and I think we've gone through most of the aspects of evolutionary architecture kind of at a high level, But what are some of the things that we've missed? What are the other aspects of evolutionary architecture? What should people check out if they're interested in this idea?
We're almost finished with our book, which should be out early 2017. And we do a deep dive on the things that it takes to make an architecture evolvable, including an entire chapter on coupling and cohesion, starting at sort of the source code level and moving up through component and service level cohesion and coupling, because we have found that that's a really critical thing to really understand architecture, and especially moving and restructuring architecture, understanding the coupling points and what we're calling appropriate kinds of coupling, because you can't build software without coupling things together. I mean, you have to use operating systems. You're not going to build your own operating system, and if you're using that, you're coupling yourself to it. And so the real trick in software architecture is finding the appropriate levels of coupling that do the things you want, which reduce duplication and create places where you don't have to do silly things like, go around and change the same thing on every machine, but don't create inappropriate levels of coupling that prevent you from evolving your architecture. So we go into a lot of discussions about exactly what are appropriate levels of coupling and how to try to achieve that. And we talk a fair amount about these engineering practices around incremental change, excuse me, that allow you to both do development in this architectural style and also do operationally this kind of architectural style.
All right, Neal. Well, thanks for coming on the show. It's been great talking to you. I enjoyed the YouTube videos I was watching to prepare for this and reading some of your slide shares and stuff. So it's been great having you on.
Great. I appreciate it. It was a great conversation.
Software Engineering Daily is having our first ever meetup in San Francisco, January 11th at Galvanize. If you live in the Bay Area and you listen to Software Engineering Daily, please come check it out. I would love to meet you. We're going to have some awesome speakers. We have Pete Hunt, who is one of the early members of the ReactJS team, who is now the CEO of Smite. Hasib Qureshi, who has been one of the most popular guests on Software Engineering Daily. Preeti Kasireddy, who has written about her career transition from venture capital to software engineering via Coding Bootcamp. Each one of these speakers is going to give an awesome talk, and I hope you can make it January 11th at Galvanize in San Francisco. You can sign up on meetup.com. You can also find the link on the Software Engineering Daily website, softwareengineeringdaily.com. I really hope to see you there.